What we're going to do today, we're going to try and see the different ways in which you can engineer a small thing like a rocket and make it fly. All right. So we've actually worked around with it, and we've worked out a way in which we can make a small bottle go about, I don't know, 20-30 feet or so. But it takes a little bit of tweaking. So we can actually work through the tweaking and see what works and what doesn't work. Does that sound good? Yeah? Okay. Is everybody here? Okay. So what I want to start out with is a everybody can hear me? Yes. Okay. What I want to start out with is a small discussion about fuels. What do we know about fuel? What kinds of fuel do you use every day? What kind of fuel do you think we can burn?
Okay. So if you've got a liquid, you then have the appropriate temperatures and pressures at which it will then vaporize. Then is the explosion greater or is it lesser when it's in a gaseous form? It's greater. So what you have to do is wherever you store the product, like last night, we started off with alcohol. Right? We then shook it. Well, okay.
Rephrase.
Industrial alcohol. All right, that's even worse, maybe. But we vaporized it. Go on, you explain it.
Sorry. So what we did yesterday, we tried burning some alcohol, right? So alcohol we have in our lab is stored in its liquid form. When you burn it, it burns with a clean blue flame. It only produces carbon dioxide, doesn't produce anything else, and a little bit of water. So we thought it would be a good fuel, but it wouldn't work in its liquid form, because in its liquid form it wouldn't generate the kind of heat and pressure that you need for your projectile to go up. So you need to vaporize the alcohol. So what we did actually, we took a bottle full of it, a bottle just like this one, and then we poured some in and shook it around. So the more you shake it, the more it vaporizes inside because of the friction from the heat. The heat from the friction. Yeah? So when you do that, all of it vaporizes, and then you drain out the excess, and so now what you've got inside is just alcohol vapor. Yeah?
Which is lighter than air.
Which is lighter than air.
So therefore it doesn't come out of the bottle when the bottle's upside down.
So then, theoretically, you could just plug in a match here and have it set it on fire, and this should then go up. Because all of the fuel will burn, that will expand the gases inside, and there will be pressure released from here, so it should go up. Yeah? It did go up once. And then it stopped working after that. Alright, so now we've tweaked that problem and we've come up with a different fuel. Okay, so we've come up with a fuel which is hydrogen. How many of you know what hydrogen is? Where in the periodic table is it? I like this class. I really like this class. They're better than a lot of my 11th standard students. Okay, but what we are going to do, which is more interesting to do, is we'll make our own hydrogen. So what I've got here is very strong acid. This is, you can see the fumes of it, right? This is, that's why I'm holding it this way. This is hydrochloric acid. Hydrochloric acid, when it reacts with any metal, what does it do?
Release hydrogen.
It releases hydrogen, and it forms a metal salt which stays back in the solution. Okay. So what we're going to do, so if you want to
Control means?
Just to show.
So we'll work with small volumes and then work our way up and see how that goes. This is zinc metal. It's a transition metal. It's very shiny. It is soft. It bends easily. And I'm going to mix it with some of this acid, and it should produce hydrogen. Okay. So I don't know if you'll be able to see it from there, but gas will be produced, and we'll trap that gas in the bottles that we have here. Okay. You see that?
Yes.
What we also found out is that the amount of fuel we use inside, that should technically take this up, but it doesn't take it up very high. So at least in one trial, when we fired it, it came up till here and then fell down. So it wasn't very good. So we're trying to fill in as much hydrogen as we can. So what we have here is a setup where this is your normal gas lighter. We've extended it and got a wire here. So when I spark this, there's a small spark produced.
Can you see the spark?
Yes.
Or can you want a spotlight turned on?
Okay. So to hit the gas should catch fire, and the pressure should be released from the bottom, and then it should fly up. Does that make sense?
Yes.
Okay. So we'll see if that works. I'm going to move the acids out of the way.
That obviously is just continuing to react, but the hydrogen is then dissipating into the atmosphere, so it's not not going to catch fire. You ready to fill?
Don't be nervous.
So, right at the very beginning, you could see that the reaction was actually much stronger. So therefore, although the volume of the bottle was different, right, you probably got a higher concentration of hydrogen inside that bottle, right? And obviously the volume of the bottle, although we might have left it on for longer, because there's not so much hydrogen being produced, then it would actually take longer to actually fill it up with an appropriate amount of hydrogen.
So you see, this reaction produces heat. So the reaction mixture itself is hot. You can touch it. Which means there's also water being boiled off from this solution. So the second bottle could have gotten a lot of water vapor in it as well, right? Which would interfere with the reaction. Okay, so this is boiling some of the water off as well. There are lots of small problems which are just technical problems. You can figure this out by simply working through simple procedures, reaction mixture, and see if there was water vapor in there, and that's why it didn't catch fire. Right? There are lots of these small things you can test out whenever you are working with any system. So that's the kind of those are the kinds of experiments that you all should be thinking of. What are the small problems that you can find, and how do you fix those problems? So as a demonstration, I want to show one of the problems we found. So we thought that the diameter of this neck is much bigger than the diameter of the pipe we have here. So we wanted to make it fit snugly, right? So we wanted to have a pipe which would fit it almost exactly. So our thinking was that if we have that, it would have a better reaction, and it would fly straighter.
The propulsion would be better,
right?
Because obviously there's more difficulty for the air to get out.
So that's our prediction.
Just out of interest, one of the things that I often have discussions with kids, we hear that plane going across. What is it that makes that plane stay up in the air?
Turbine.
Fuel?
Turbine propulsion.
Aerodynamics.
Right, the aerodynamics. What pushes an aeroplane, or why is it that as an aeroplane goes along the runway, eventually it goes up into the air?
Because of the aerofoil shape of lightweight.
Lightweight? It's not. Weighs
Streamline
tons.
shape of the airplane, and also the lift.
Okay, so keep on talking. The aeroplane, the wings, the body. What makes it go up into the air? Okay, what about the lift?
Bernoulli's principle.
Pressure difference.
So what pressure is there? Is there high pressure, low pressure? What pressure?
On the wing it is low pressure, above the wing it is high.
Right, so obviously if you're wanting a plane to go up into the air, the pressure above the wing has to be at a lower level than the pressure underneath it. And what you actually do, if you look at the cross section of a wing,
It's at
you'll see that it's got a hump in it. The one underneath has got a bowl and then it dishes. What it actually means is that the air going above, as the plane goes faster and faster through the air going across the top wing gets stretched. Okay, so that becomes a lower pressure. All right, so therefore what actually happens is that over a period of time, as the plane is going faster and faster along, then it eventually goes up. Now obviously, as we just thought, you can imagine that the pressure on that, as it goes faster and faster, will try and get the thing to take off. All right, and so obviously they don't want it to do that, so you have to be very careful in the design of the foils and stuff like that to keep it down onto the ground.
And we'll try this again.
We hope.
Hey, Flo. Hey, we can do nothing wrong today.
Not as high, but not as high.
Not as high
as the other one did.
So your hypothesis that there won't be enough oxygen is not true, right? There is enough oxygen for it to get in and for it to catch fire, but it didn't go as high as the earlier one.
What we could do is take that off.
Also, you notice that between each flight, I'm airing this out. Why am I doing that? So when hydrogen burns, it forms water, which is trapped inside this. You want to remove that so that there is more oxygen in there, so the new hydrogen can burn again. Okay.
Why might I break this zinc into smaller pieces?
Yeah.
Why would it cause a faster reaction? Is it smaller? What is there more or less of that makes it have a faster reaction? Huh?
Surface area.
Surface area, yeah. All right.
Also, what's the problem with the way that we are doing this experiment? So we are trying to test out differences, but there's a problem. What is the problem? What are we not thinking about when we are doing this?
amount of hydrogen that's into
The amount of hydrogen that's in there. So if we want to do a precise experiment, we want to design this such that there's exactly the same amount of hydrogen each time we test it, right? That was the best one yet, I think.
Well, hopefully if you were able to catch that on video, you will have seen the flame,
Yeah.
right? Which obviously then, as to whether or not, so like if you did it frame by frame, how many frames per second does it have to be to look like a movie?
24.
26, nearly. All right, good.
All right, so any theories on why this worked better than the last one?
Lack of friction because there was less surface area, so the friction was less.
Okay, there was less surface area, so the friction was less. So not surface area exactly, but the contact. So that's actually all we wanted to talk about. There's lots more that you can come talk to us about. So even the building of this spark thingy took us a while to figure out. I'm going there.
All right.
Yeah. So it took us a while even to work out how this thing, because it wouldn't travel up from this wire to here. So we had to work out the conduction within the wire, so that it would not spark here, but it will spark here. An interesting question to answer is whether the mass of the bottle being less is enough to make it go higher, or because this is a bigger bottle, there's more fuel to burn. So will that work better? That's an interesting question, and my guess is that it will work at a non-linear sort of. So if you were to plot the graphs and do an exact this thing, there would be one particular point at which the mass and the volume are the optimal for it to go the highest.
What's the gap now?
3, 2, 1.
So what do we think the problem was with this one?
It was
Mass. Right, because the friction wouldn't be the problem because it's the same diameter as the other bottles. So it's probably the mass. So you need more hydrogen in there.
Come on, Chrissy, come on. You have to do it. Wow, Chrissy, you done it.
My question to you all is, can you improve this design? Can you make it go higher? Can you come up with fuels which are better, which make it go further? One is that. The other is, can you come up with a better design where the friction on this, even though it fits snugly, the friction on it is less. Okay, so you come up with designs, and if you come up with good solutions and feasible solutions, we'll help you work that out, won't we? Yeah. All right. Thank you.
Thank you.
I hope you had fun. Okay.